Okay, we talked about basic antennas, vertical and horizontal. So we'll talk about some of the directional antennas, which give you more gain in a specific direction.
Okay.
So you don't have any power gain. If I put 100 watts into the antenna, I'm still getting maybe 100 watts out, usually less. But if I can concentrate it in one direction, I have more power per square centimeter. So we specify the gain of the antenna in decibels again, and we normally make that relative to some reference. Uh, there's this thing called an isotropic antenna. It's a theoretical antenna that's a point source. Think of it kind of like a light bulb,
Okay.
and it radiates in a 360 degrees pretty much. Well, that's what an isotropic antenna would do if you could actually build one. So it has no gain. It's basically zero because it's you know, a full hemisphere. Um, we also reference a dipole because it's the basic antenna, and we use dBi for the isotropic and dBd for the dipole. And it turns out that a dipole has 2.15 more gain than an isotropic antenna. So you need to remember that 2.15 number. Now, a lot of times when manufacturers for antennas will list their specs, they'll do it in dBi because it's a bigger number. It doesn't mean it has any more gain. It's just, part of that marketing stuff they do because they use the biggest number. um, we also specify in a directional antenna the front to back ratio, where it's the ratio of the power in the forward direction versus the power in the opposite or rear or back direction. And sometimes that can be as much as a 20 dB ratio. What you try to do on a directional antenna is minimize the rear lobe as much as possible. You want to try to concentrate all the power into the forward lobe. When we talk about bandwidth of a directional antenna, it's the range of frequencies over which the return loss is less than 3 dB. In other words, it's where the power is half of what the maximum power is. And all the frequencies between those 2 points uh, give you the bandwidth. So we call those in like filters and things upper and lower cutoff frequencies. So the difference between those two frequencies would be the bandwidth. Typically for a directional antenna, that's going to be fairly narrow, maybe only 2 or 3% of the center frequency. Now, if you use larger elements for the antenna, it will increase the bandwidth. It will also uh, cause you to have to shorten the elements because making the elements larger makes them look electrically longer. So you have to make them shorter if you do that.
Question.
Okay.
Question regarding that. It's so your bandwidth is increased by using larger diameter elements.
Right.
What would be an element?
Oh,
What am I using? A rod, a string, a wire?
your wire, or
Okay.
in the case of most directional antennas, um, they're going to be metal, aluminum tube or rods typically.
I was just trying to figure what defined the element.
Yeah, it's the actual, um, like in the half-wave dipole,
What you're connected to.
those two wires are the
Uh,
elements of a half-wave dipole.
Understood.
Normally that's wire, particularly at the lower frequencies.
Okay.
It'd be hard to have a tube that long and suspend it.
Yeah. All right.
Um, this is this showing of the front to back ratio, where we have the forward or main lobe versus the back lobe or the rear lobe. So that the ratio of the length of this lobe to that lobe is what we call the front to back ratio.
And just to break it down for my brain purposes, um, you're talking about having a vertical antenna with a wire or a cable or something that's, I guess, it's
No,
not so. Okay, so yeah, I'm trying to figure out what am I looking at. What is my back power, my front power? Oh, how do I decide where my main lobe and my back lobe are going to go? Like, what makes that decision?
okay. Imagine this, whatever this thing
Mm-hmm.
is your antenna.
Right.
Well, let's say it's a halfway dipole.
Okay.
Okay,
Vertical. Mm-hmm.
just happens to be vertical, but if it was horizontal, it's the same thing. We'd be looking down on the main lobe. So we learned that a normal halfway dipole is going to have a radiation pattern
Right.
like that, right?
Right.
Okay. If we add a reflector over here,
Okay.
it's going to reflect the signal
Understood. It's going to
back and
bounce
it's going
back.
to add, and we're going to get a lobe like that and a smaller lobe like this.
That's what I was wondering how you controlled that. Okay, I understand now.
If I start adding what we call directors out here, they tend to receive and kind of retransmit the signal, and it adds at certain points. These are precisely spaced for that phasing to occur. And the more of these you have, the tighter this beam can
Be focused.
becomes. The more
Understood.
gain you get in the forward direction, the
Hmm.
less you get in the rear, and it may or may not reduce the side lobes.
Okay, so it basically focuses it
Right,
into one. Right. Okay.
right. Now, like that would be typically your Yagi antenna would be like that. um, you can do it horizontal or vertical.
Okay. Thank you for breaking that down for me.
Okay, here's a Yagi.
Hmm.
Okay, this is the driven element, which is a half-wave dipole.
Okay.
This is a reflector. It's a little bit longer on
Okay.
purpose. It
To
looks
catch fog.
capacitive and it reflects the signal back.
Right.
Uh, and then these are driven elements and they're shorter.
Because we're
Now,
focused.
and this was developed by two guys, Professor Yagi and
Udo.
Professor Udo,
Udo.
who actually, and Udo or Odo, whatever it was, um, actually did it, but he worked for Yagi, and Yagi got all the credit. Uh, so it was called a Yagi antenna, but they're starting to recognize uh, the guy that actually did it. And you put these elements on a boom. It turns out that in the case of the Yagi, the reflector and all of the directors can be connected to this boom which can be at ground. So
Oh,
all
okay.
electrically connected. Now, depending on how you feed the driven element, it may or may not be connected. And we'll go into that in a little bit.
Thank you for spoon feeding that because I've always looked at one and never understood how it works. So I appreciate that.
Okay. So the key thing is the driven element is approximately a half wavelength. The reflector will always be a little bit longer,
Right. To
usually a
catch.
few percent, and the directors will always be shorter. Now, the official calculations, if you go to there's lots of websites where they have Yagi calculators, and you put in the frequency and some stuff, and it'll tell you the uh, length and spacing of all the elements, and they're variably spaced, and the length of the directors changes. It turns out there was a thing done by John Portune based on some old NIST studies back 40, 50 years ago. You actually can space them equally at a quarter wave, at a 0.2 wavelength, and make all the directors the same, and it'll only affect the gain by 1 or 2%. So you don't have to go through all those calculations. You can kind of do it on an envelope. The main thing about directional antennas, they tend to be high gain. That's the whole purpose. Yagis can be up to maybe 20 dBi. Remember, I said dBi, not DVD, so it would be slightly less than 18 dBd. Can have a front to back ratio of up to 20. Very narrow bandwidth, only a few percent. And if you use larger tubing, you can increase the bandwidth. It also makes it heavier. So there's always cons to everything because these booms can get pretty long, so you have to support them. And if it's on a rotator, since it's directional, you almost need it on a rotator to be effective. uh, it's a much higher wind load, so it requires a bigger rotator and stuff like that. Um, you can kind of tweak a Yagi. Uh, so by adding more directors and obviously increasing the length of the boom to support them, you can increase the gain up to a point where it becomes diminishing returns. That's why it's limited up to around 20 dBi. Um, at that point, every time you add a director, it's like up, you know, half a dB or a tenth of a dB. It's not worth it. You can increase the bandwidth by using larger diameter elements or tubing usually to reduce the weight. They could be solid rods, but usually use tubing to make it lighter. You can optimize the front to back ratio and the forward gain by adjusting the length of the boom and the number of elements and the spacing. So you can start playing with the spacing of the elements, and it will affect the side lobes and the rear lobe. So there's all kinds of little things you can tweak depending on what you really want, if other than just maximum gain in the forward direction. And maximum gain in the forward direction would not give you the highest front to back lobe necessarily. Typically, it's going to look like something less than 50 ohms, so you need some kind of matching network. One of the more common is called a gamma match. It's hard to see, but there's a Greek letter called gamma, which is kind of that shape, which is where it got the name. And it consists of uh, a rod with some insulation on it that's connected to the center conductor of your connector, which goes into a tube that you can adjust the depth of it, which is controlling the capacitance. And then there's this shorting bar, which you can also adjust where it is. So you're feeding the driven element off center. So what happens when you go off center? You increase the impedance, right? It's also affecting the inductance, which is why the variable capacitor is here to offset the inductance of where this is. So you can get a very close to a 50 ohm impedance when it's adjusted right. The other thing about using the gamma match is the driven element does not have to be insulated from the boom. It can be a solid piece, approximately half wavelength long, that's connected to the boom, which is normally grounded, because you're feeding it between the center point and this short out here. The other common one is called a beta or hairpin match. Again, it's to give you 50 ohms. And it's a piece of transmission line stub. Doesn't necessarily mean it's coax. It could be, but it's harder to do. Normally, it's two parallel wires bent in a U shape. So the length of them is going to be something less than a quarter wavelength. And the spacing is going to be such that it gives you some impedance like 50 ohms, 450 ohms. You can calculate what it is with that formula because you know the size of the wire and the spacing. And with that, you can figure out where this short needs to be, because the impedance as you run the shorting bar along it will change. So you can find a spot or calculate a spot where it will compensate for whatever the impedance is of the antenna and make it look like 50 ohms to your feed line. Normally you would do this with a Smith chart or a calculator online, which will tell you what size wire to use and how long it is, what the separation is, all that. Those are the, excuse me, those are the two most common. In the beta match, though, the two driven elements have to be isolated from the boom.
So, just a quick question. On my 75 ohm coax, if I wanted to use this particular type of antenna, I would go with the gamma one so that I wouldn't have to worry about that.
Well, you could do either.
Mm-hmm.
I mean, it would change. You'd have to look at, like on the gamma match,
Mm-hmm.
how long that tube needs to be and
Right.
stuff to get it to match 75 ohms. And
Okay.
then you're still going to have something to match your 75 to your transceiver
To my
at the radio end.
but you were saying the transceiver, I could get one that would be able
Yeah,
to optimize itself, but with the 75.
yeah. And it's
Yeah.
probably got a tuner, what they call a tuner built in, which is just a matching device.
Mm-hmm.
So as long as you were within an SWR of 3 or less,
Mm-hmm.
the auto tuner in your radio will match it.
Okay. I'm just trying to put together what you're telling me and what I'm attempting to do so that it makes sense.
Okay.
Okay. I got you.
Now this is a picture of stacked Yagis. Okay. So they're more than a quarter wavelength apart vertically. So what that does is the two beams kind of merge and it narrows the beam elevation wise. It still has the same width, but it's narrower vertically, which actually puts more power into the beam, and it gives you a gain of about 3 dB above a single Yagi.
So, in other words, instead of making it wider, we made it taller and centralized it that way.
Well, no, you made it thinner instead of taller.
Well, that's what I mean. Like, instead of making it wider,
Right,
we just stacked it and made it taller, but yet still centralizing the same position.
right. Now you
Okay,
notice on this one, the driven element is actually a folded dipole,
I saw that.
which isn't uncommon, because the folded dipole will give you 4 times the impedance of whatever it would normally be.
Which isn't what you're looking for, is it? Don't you
Well,
want less impedance?
it depends. It might be easier to match.
Oh, that's true, depending on your equipment. Okay, I get
Yeah.
you.
Okay, so we learned on directional antenna, we specified the gain in dB, usually dBi relative and isotropic, or dBd relative to a dipole, and dBd is 2.15 dBis. So if they use dBi, it's because they want to make the number look bigger. The bandwidth is the range of frequencies between the two 3 dB half power or 3 dB points. Uh, it's typically pretty narrow. Larger elements can increase some, but there's a practical limit on how big you can make the elements. Um, the front to back ratio is just a measure of the relative power between forward and reverse. And the major lobe or the main lobe, same thing, is the direction in which the maximum radiated field is measured. So it's usually that forward lobe, and it's the peak of it when you look at a azimuth plot. The Yagi is probably the most popular of the directional antennas, although there's quite a few variations of directional antennas. Um, it's a multi-element, at least 2 elements. You need a direct driven element and a reflector to make a basic Yagi. Typically, it's going to be 3: driven element, reflector, and a director. And that will give you maybe 6 or 8 dB. Uh, the driven element is approximately half wavelength. Reflector will be longer. Directors will be shorter. And you can optimize all those things by playing around with the length of the boom, the number of elements, and the spacing. The gamma match, the main thing is that you don't have to insulate the driven element from the boom. It does make it easier to build the antenna. It's a little more complicated to make the gamma match than it is something like a beta match, where that's just a bent piece of wire. Um, it's affect a parallel transmission line that's shorted at a certain distance to give it the impedance you want to provide the matching. We call that a conjugate match. What you're doing is coming up with the opposite impedance of what the antenna has, so the reactances cancel out. So, which of the following would increase the bandwidth of a Yagi?
Alpha.
Uh, yes, alpha. Alpha.
Now, it's interesting because I could also say that a tapered diameter element would increase it, not as much. And you see that a lot the way they're built, as they tend to get long, where they'll use a larger tubing close to the boom and then maybe a smaller tube out for a while, and then maybe a solid rod or tube out, just to make it stronger so they don't droop as much. But that
Okay.
also gives you the effect of a slightly larger element, but A is the correct answer for this.
Okay.
What's the approximate length of the driven element of a Yagi?
I thought it was
The half wave. It's
the
Bravo.
Bravo. How do the lengths of the three element Yagi reflector and director compare to that of the driven element?
The electric long. Alpha.
um of the three element Yagi reflector and director compared to that of the driven element. Yes. Yes, alpha. Correct. Yes.
How does the antenna gain stated in dBi compare to gain stated in dBd for the same antenna? Read this carefully.
Yeah.
1.5
Is
high.
the dipole and the I is the light bulb one. So
It's
So
the Bravo because 2.15 decibels
higher.
higher in
Yes.
the for the dBi, right?
Correct.
And
correct.
that what you said? Yeah. Okay.
Yeah.
They tried to trick you.
They did. They don't need to.
I know.
What's the primary effect of increasing boom length and adding directors to a Yagi antenna?
Well, that was the whole purpose, the gain to increase.
Right.
Okay.
What does front to back ratio mean in reference to a Yagi? Actually, it's the same for all directional antennas.
Charlie.
Yes, Charlie.
What is meant by the main lobe of a directive antenna?
That's where it's maximum
Current.
radius. Yeah.
Yeah. So
So,
Bravo.
a delta.
Oh. Okay, wait, let me read it again then.
That's the maximum radiated strength from the antennas going out the main
Correct.
lobe.
Not the radiation. Correct. Yes. Delta.
Whew. Okay.
In free space, how does the gain of two three-element horizontally polarized Yagi antennas spaced vertically 1/2 wavelength apart typically compare to the gain of a single three-element Yagi?
Uh
think
I
you
think
said
I,
that in passing.
yeah, we didn't really focus on that too hard. So,
3
is it
decibels, I think, is what you said. Bravo. No. Yeah.
so
Oh well.
of two, three element horizontal, so that's going to be twice as much, right?
right?
So would that be Bravo? Yeah.
Is that right?
3 dB.
Because they're both at 1.5 apiece.
Yeah, I think I said quarter wave apart. They're half wave apart.
Yeah.
My bad.
That's all right.
Which of the following can be adjusted to optimize forward gain, front to back ratio, or SWR bandwidth of a Yagi antenna?
Elements. So it's the first two are correct. So delta.
Yes. Yes, all of it.
What is a beta or hairpin match?
The stub. So it's alpha.
It's the shortened transitions to place. Yes. Alpha.
The stub is the important because
Yeah.
that's how you said it. Stub.
Which of the following is a characteristic of using a gamma match with a Yagi antenna?
Does not require the driven element be insulated. So alpha.
Insulated alpha, yeah.
Ooh,
Okay.
Yay! That was so much easier than the last one.
Well, just wait till the next one.
Oh
oh,
no.
great.
That's a warning.